All right, folks, let's start. All right. So I want to do just a little more assembler, and that'll be it for today. They'll go up to the lab and help anybody who wants to work on their stuff up there. So here's some simple instructions. Move is your most common instruction. And by the way, a guy proved about a year ago that move is NP complete. You can compile any program into just move, 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 move. It's pretty horrible. And by the way, there were some TGF problems like that because you pretty much, there's no point disassembling it. You'll never figure out what's going on. You can make an if out of a move by doing an illegal move, which triggers an exception, and you move an address into the exception register, like, man. So it's, anyway, that's just for fun. Normal humans only use move to move data around. So here's the two formats I mentioned before. The Intel format, typically written in capitals, where you have the destination first and then the source. In the AT&T format, you have source destination. So like I say, my rule is find an immediate value, and that has to be the source, because you can't move something into 48. You can only move it into something like ESP or EBP, or bracket 48 would be okay. That would be address number 48, but you can't move into this, so that has to be the source. Anyway, those are the two formats. Windows people typically use Intel. Linux people, well, I think Windows people use AT&T and experts can tell. Also, the AT&T one has this letter at the end that tells you if it's a long or short amount of data being moved, which the experts can tell, and I just don't worry about that level of detail very much. All right, and remember indirect addressing, so brackets around anything, you can take that, interpret it as an address, and go to that memory location. So here's move EBX to EAX. This will take what's in EBX and put it in EAX. Here's move 42 in EAX. Here's move the contents of this memory address, 4037C4, and put it in EAX. Here's take EBX, interpret it as an address, get the memory from that address, and put it in EAX. And here is take EBX as an address, add 4 times ESI, and get that contents of that memory and put it here. This is a very common construction to do things like copy a string, because remember, each data is stored in a word 32 bits long. So if your first thing is at location 1000, the next word is at 1004, the next one is at 1008, 8 bytes ahead. So you often want to count by 4s. So you'd have a loop where EBX is the start of the string, and ESI is counting through the bytes in the string, and this is how you move the 32-bit words one by one from one place to another. This is string copy, which is our friend. Most of our exploits are going to involve exploiting string copy, because string copies are usually what causes buffer overflows, as you copy something into a destination that's not big enough. Here's the thing called load effective address, which is kind of nuts, where you do a calculation of an address, but then you don't get the memory from that address, you just put the address itself into here. It's just a fancy way of doing an add. I don't know why it happens, but it is preferred by some compilers. All right, so that's the game here. If EBX points to this location, then bracket EBX would be get the memory from here, which would be zeros. All right, sub subtracts, adds, increment by adding 1 to whatever you're pointing to, decrement subtracts 1 from it. Very commonly you have loops, load something to a starting value, do something, decrement. If not 0, do it again. After a while, you decrement it to 0, now the loop is done. That's how you implement a loop. You have multiply and divide, very rarely used for anything we care about. They are available early. When I did this game, there was no multiply and divide. You'd have to write your own code for that. But they exist now, but the only people who would care about that is people doing like 3D rotations of graphics or something, typically. Not does nothing. This is like stupid and insane, just like 0. And as you know, 0 turned out to be super useful in arithmetic, and not turns out to be super useful in programming. Now, the normal reason why you need not, remember that instruction we did an hour ago where I moved 42 into EAX and it took 5 bytes. So 5 bytes to that instruction. Now, it turns out that a lot of instructions do not like to be stuck on odd parts of memory. They want to be at the start of a word. So if you put a 5-byte instruction, you're not supposed to put the next instruction right in the 6th byte. You're supposed to skip to the 8th byte. So you have to fill 3 bytes with something, so you fill it with NOP. It's the filler to make things line up correctly. But NOP is just an instruction that does nothing and goes on the next instruction, and turns out to be extremely useful for attacks. You're going to be using a lot of NOP. Because, remember, the fundamental idea is you find a memory corruption, you change EIP, now you point EIP to what you want to execute. It's going to turn out that you can make mistakes, and the operating system can have different versions and various products running that change the addresses, so you don't really get the right result for the address, but you're close. So then what you do is you take your attack and you put like 1,000 NOPs before it. And if you hit anywhere in the NOP sled, it will go NOP, 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 and do your egg, which is your attack. So NOP sleds are very common in attacks, so much so that some network defense products actually look for any packet full of NOPs, and that's an attack. So if you want to be a little clever, and Metasploit will let you do this, you don't really need to use NOP for NOP. You could use some instruction that doesn't matter, like increment EAX, when I happen to know I'm not using EAX, so I don't care. So I'll just increment it 1,000 times, it doesn't matter. There's plenty of instructions that do something relatively harmless, but they aren't equal to NOP. But NOP is the most common NOP instruction used to pad things. So the stack is extremely important. It's what you use to store local variables that are used in one routine, and the most important thing for us is it's what's used to go into a subroutine and to return to the calling program when you're done. The step where you return is the dangerous step that lets you take over the machine in most cases. So you put things on the stack with push, you remove them with pop, and the stack frame, which is the stack used by the current subroutine, goes from the ESP to EBP. That's how big it is. So you can call to get into a subroutine, and that will enter it and form a new stack frame and have local variables. And then when you're done, it will do leave or return to come back. And that will pop stuff off the stack and restore you to the previous stack condition. So function calls are things like printf. You're doing something and now you want to print something. So you call printf. You're in main, for example. Some data asks the user something. Now it's time to print something. I stop executing main, and I call printf. I go down here and do some printf code, and when I hit the return, I go back to here, restore the previous condition, and continue where I left off. That's the game. So when you first enter a subroutine, there is a prologue, and the prologue is how you remember what you were doing and save it for later on the stack, and set up a new region of stack memory to be used by the subroutine. That's what the prologue does. Then, at the end of the program, you have an epilogue, which removes all the new stack you added and restores the condition of the processor back to the way it was in the calling program so it can resume. That's the game. So here's how it looks. You might be in printf here, and when you went in printf, it added a new frame on the stack. If your main was here, so here's Windows, colors. I'm in Windows, I double click something like Microsoft Word. So it launches the main routine of Word, and that is a child of the Explorer process that draws the desktop. So this stops running at this point and executes a subroutine, which is my Microsoft Word. Then Microsoft Word tries to print something, so it calls a subroutine down here. Now I'm 2 levels down. While I'm printing, I'm using this. When I hit the epilogue, it will it'll pop this stuff off the stack, change the stack pointer back to here, so it can resume this, and that stack is not erased, but it's no longer used. It will just be overwritten by the next function I call. That's why the stack is perfectly designed for this process. The reason stacks are in computers is because of this idea of having function calls and functions that call other functions that call other functions. You can stack these as high as you want until you run out of memory. And as you can imagine, you're typically dozens of layers deep in a modern operating system. So inside each stack frame, it stores your local variables. There's the things that are defined inside the subroutine, used only in the subroutine, and discarded when the subroutine ends. So they're stacking up here. And you can test things. Test will test 2 values, and all it does is, if it's 0, it sets the 0 flag. So you test, and then you do a jump 0 or a jump not 0. That's how you execute an if. All right. JZ jumps If the zero flag is set, JNZ jumps if the zero flag is not set. So with increment and JZ and test, you can make a loop. You start at 10, decrement, jump 0 here, jump not 0 back up there. You know, there's a lot of ways to do it, and your compiler will choose a mixture of these instructions to create whatever code you pivot. So every C program starts with a main method, and the main method has arguments. argc tells it how many arguments you have, and argv is a pointer to an array of names that contain the arguments. So that's how you pass data into main. So if I copy foo to bar, CP is a program written in C. Every unit command was written in C, pretty much. So this will copy foo to bar. The argument count is 3. The name of the program is 1. The first parameter, the second program is 3. So argv 0 is CP. The first argument is foo. Next argument is bar. And now it enters main with those parameters and executes a copy routine. It creates a new file and moves the contents of one file to the other. So here's ways to see things look like an assembler. So you might have a number, define it as an integer, and then increment it. So in assembler, you write it this way: number define word 0. This will define a 32-bit word that can store an integer value. And then you move number into EX. You can't increment RAM. It might make sense, but you don't have that instruction. This is why I say I used to do like self-modifying code back in the old days, because 8-bit processors had a very limited set of instructions. And very often what you want to do is not available. And you have to find some way to combine the instructions to add up to it. So I just want to add 1 to this number. There is no increment RAM location. You have to copy the location into EAX. This name number means that value. Then increment EAX, then put EAX back in number. That's how you do it. It takes 3 machine language instructions to add 1 to that number. You can't add in place. You can only add on the chip in the registers. All you can do with RAM is read from it and put it on the chip, or take stuff from the chip and put it in RAM. You can't change stuff in RAM with things like increment and decrement. That's why the registers are your temporary storage location. You are constantly reading stuff into the registers, messing with them, and putting them back on the memory. Right, so that's the game. So here's incrementing. If I want to make a loop where I'm going to have if statement, number less than 0, do something, then it's not incrementing, it's an if statement. So I have a number. Now I can't do if the value in memory is 0. Again, it might sound good, but you don't have that option. You have to put it in the register. So include it in the register. Now one way to see if it's 0 is to do an OR instruction. OR EAX to EAX, that will be 0 if the number is 0. That's one. Now each compiler will have to do something with it. They would set the 0 flag and then look for the 0 flag. And there are many instructions that will do the same thing, like test. And each compiler just has an arbitrary decision made of what it does. So this will combine them and then jump greater than or equal to label. That's one way to do it. Here's an array. I'm going to define an array with 4 bits and then set the second one, 4 words, 4 characters, and set the second one to 9. So here's how you do it in assembler. You define words and put in 4 zeros, and then you put a 2 in EBX, and then move array plus EBX. 9. And I don't think you're allowed to put the 2 here directly because that instruction just doesn't exist. That's why you have to go through this 2-step process of first putting in EBX. It is very often the case that the particular combination you want is not available. You can only do this with registers, so you have to first put something in a register. And 32-bit assembly code suffers greatly from not enough registers. You waste a lot of time saving the registers, putting junk in the registers. 64-bit code is much more efficient, not only because it moves 64 bits at a time, but because there are a lot more registers. So very often you can do what you want easily with registers instead of constantly having to reuse registers over and over. So here's a triangle. I define a triangle of width and height. Then I calculate the area of the triangle, width times height. So here I set it up, and the only thing I thought was interesting, you actually use this integer multiplication command. So you have to move everything into registers, then you have to do an integer multiplication of it, and then you have to take all the junk in registers and put it back in the memory. Anyway, so I got a few cahoots, and that's enough of this to get started. And I'll just point you to the project, which I think is no surprise to you guys because you've taken my classes before. But let's see, the cahoots are around here someplace. Next tab. There, those look cahooty. Let's see if I found these cahoots up or not. I was in a hurry, I didn't check them. Okay.
They need to mix up some music.
About that?
They need to mix up their music, so it's not always the same.
Well, you know, I consider the price of it. If they go broke and I have to write my own code, I was thinking I'd put in my own music, but you know, I'm not energetic. Well, you can do it. Probably pretty easy. A little PHP, a couple wave files. How hard can it be? I don't know. All right, I'll take another 10 seconds. All right. If it was me, I'd make it the Jeopardy music. Da, 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 da. What term describes the instructions at the start of a function? Because I don't care what I'm talking about. I was totally wanting to replace all the Jeopardy music. Okay, that's the prologue. The editor function, that's what prepares your stack so you have a local stack frame to work with. All right. What mnemonic enters a function? All right, that's call, okay? You call printf or something, all right? You might multiply two numbers. Okay, I model the first integer multiplication. All right, what mnemonic compares two numbers? To see if they're equal. All right, that's test. All right, and there we go. What mnemonic serves a special purpose and buffer overflows? All right, that's not, does nothing, and you'll often have a big string of them. And what mnemonic shrinks the stack? Okay, that's pop. It moves the top entry from the stack, and that makes it smaller. All right, so here are the winners, which is Brandon has 2.
It would have been 3 in a row, but you messed that one up.
Yeah, and Tip, I know that. And there was a third person, John E. is a new one. All right, so let me just, I'll save that. John E. will have to tell me who they are in a minute. Let me just point out, there is homework. I had some guy actually take one of my classes and say, well, I didn't get an A, because all he did was the online quizzes. Right. Well, you know, there is homework. So be warned, there's homework, and it's down here, and that's where the real fun is. So first is one you might have already done in my other classes where you use Heasman to do some simple assembly language. Heasman's a little fun simulator that makes it very easy to practice using these instructions. In case you haven't seen it, let me just bring it up. Heasman is here. And as I mentioned before, the original version of Heasman is politically incorrect. So if you have tender sensibilities, I actually made another one here without the cheesecake. Because I had teachers, I taught this to teachers, and they said, I can't use that. Look at that, oh my God, we'll all get fired if we have this pornographic product in our school. So anyway, this is made by German students to learn assembly language. And you know, they don't have American concepts of political correctness, which are pretty ruthless these days. So anyway, now you can practice assembly language. Like I can do a move EAX 10. And 19 is fine, and you'll see down here, it shows you what's going on. Move, destination, source, and it tells you a bunch of things about it. So there it is, and if you mess it up, like there, it tells you here, invalid parameter, must specify register, a memory address, or an immediate value. So it helps you. So I can move EAX 10, move EBX 11, then increment EBX, and then, oops, better spell it right, EBX, and then like push EAX, and push EBX, and pop into ECX. Now this might be a little confusing. When you pop, you don't say where it comes from the stack. You say where to put it. Pop the top value from the stack and put it in ECX. So let's run this step. Now I can run this code all the way to the end, but I can run it step by step here. So here's the registers, EAX, you're going to get real used to seeing this chart. This whole class, you're going to be running nothing but debuggers and looking at this chart. So get used to it. Your best friend, the important stuff is down here. EIP is the instruction pointer. Right now it's pointing to 0, that's the instruction to execute. EBP is the base of the stack, ESP is the top of the stack. They're both 4096 because I have nothing on the stack yet. And up here is A, B, C, and D that are just used for any purpose at all. And you use them a lot, but they don't have any great significance. And here's these sign and parity and stuff, flags that we don't really need to worry about. So now if I execute the first command, move AX 10, it puts a 10 in the AX. Then I got move EBX 11 here, okay. Then I increment EBX, so now it goes up to 12. So that should all be pretty clear. Now I'm going to push EAX onto the stack. So I do that. Nothing happens over here, but it's going to go on the stack. Here's the RAM. This processor has 4096 bytes of RAM. And this is addressable memory. The stack is at the bottom, so it can grow up. So there's the A I just pushed on the stack. It's decimal 10, but in hexadecimal, it's A, and it took 32 bits because it's a 32-bit processor. So when I put 10 on the stack, it puts on 00000000A. So now I'm going to push EBX on the stack, and you see the C appears down there. Now I'm going to pop ECX. Right now ECX has 0. When I pop into it, the 12 goes in there. Now notice the C remains on the stack, but the stack pointer changes to 4092, 4096. So it's leftover data. The C remains on the stack, but it's not pointed to by the stack pointer, so it's going to get erased later. Next time I push something else on the stack, let's do that. Let's push like a 1. Okay, I'll push 1 on the stack, and that's going to overwrite that C. So there you have it, although for some reason my push, see here, for some reason it interpreted that as a 16-bit push, not a 32-bit push. So it only overrode the first half of that word. Now that's pretty messed up, but that can happen. Like I said, there are even 8-bit instructions, but you don't use them very often. But it is an issue, and in fact, there's some homework sites where we're going to hit some problems like that. But anyway, you can see it going, and you notice one of the many issues that you're probably aware of on computers is data remnants. There are fragments of data left around that you're not using anymore, but they're still there. And that can turn into security problems too. The most common one is dangling pointers, where you have a pointer pointing to an object, then you quit using the object, but you forget to delete the pointer. So later on, I can put data that writes to an area of memory that is no longer being used for that purpose. and might be being used for some other purpose, and that's another memory corruption. And in memory corruption, you're writing data where it shouldn't go, and you're hoping to hit something useful, like something that will get copied to the EIP. And if you do, then you can take over the machine. If it's boring and you just address memory that you're not allowed to address and the program stops, then it's denial of service, but you can't turn it into a remote control exploit, which is the most common case. Only a small number of vulnerabilities can be exploited. But we're going to cover the procedure used to do that. So anyway, that's your first homework, is to do some simple assembly programming in that simulator. And after that, you start doing some buffer overflows and stuff with Linux. And the only thing I want to say, we're going to use Linux a lot. We use Kali for most everything. Be sure and get the 32-bit version of Kali. If you got a 64-bit Kali, download the 32-bit version, because Linux exploits, you can't run 32 on 64 and 64 on 32. And we're going to start with 32-bit exploits. 64-bit exploits are not that hard, but it's an unnecessary level of complexity we don't need. We'll get there around project 7 or so, 64-bit exploits. And we're going to start with Linux because it's much easier. And you learn this memory. Then we're going to go to Windows, and we are going to go all the way up to exploiting modern versions of Windows with all their defenses, using the tricks to get past them all, like heap sprays and return-oriented programming and everything else. But we're going to start with the very simple 20-year-old Aleph null basic buffer overflow from the way Linux used to work long ago. That's how it all started. Then defenses came out, and fancier attacks to get over the defenses, and the Orange War went, and we're going to reproduce that history as we go through the class, getting up to modern attacks against modern OSs. So that's all I had to say. I guess there's no issue of adding or anything. I'm just going to go up to the lab. If anybody wants to work here, you can work up there. I'll be there till 4. That's it. I'll stop the share, and I'll post this stuff up on YouTube later.